Boom! We back. We ready for some more chemistry. All right. This video is about IM forces. I standing for intermolecular forces. So if you forgot about dipole-dipole, ion dipole, London dispersion, van der Waals, you have selected the right video. All right, here we go. We have four types of intermolecular forces. All right. Now, I've written them down for you like so. But wait, Miss Baldwin, there's only 3. Well, I'll explain that in just a second. First type is ion dipole. All right. Now, these intermolecular forces, let's talk about this for a second. Intermolecular forces are the forces within a solution or within a system of molecules, inside the molecule. All right, so there are forces that are kind of between groups of molecules, then there are forces within itself. For instance, I have forces within my body. My heart is beating and pressing against my ribs. Hopefully not too hard, all right? The blood is going through my veins. These are forces inside my body. I, however, can also apply a force. I can push a desk or push the computer and pull it back to me. All right? So intramolecular forces are forces that will be me, my body, pushing something else. Intermolecular meaning internal. So molecules have forces inside of them that keep them together. Some are really strong and some are really weak. So some of them break apart easy, and some of them do not because of the strength of their intermolecular force. Now, one substance that is all over the planet that has a very, very strong force is water. That's right. I think I want some water right now. All right? H2O is a very, very strong force. All right? So we're going to talk about that in just a second. And we have 4 types of intermolecular forces, forces within the molecule. First type, is ion dipole. Now, ion dipole forces are present when the compound is ionic. All right? Can y'all see my handwriting? If it's ionic, it's going to have ion dipole. Now, here's a reminder. How do I know something is ionic? It's a metal and a what? Come on now. Say it with me. It's a metal and a non-metal. All right? We can either have ionic or covalent. Covalent is 2 non-metals. But for ionic, which is what we need for ion dipole, it would be a metal. Sorry, yeah, I almost said the wrong thing. It would be a metal and a non-metal. Now, an example of a metal and a non-metal would be something like, let's get our periodic table here. Something like, can y'all see? Something like magnesium. See magnesium? Magnesium and sulfur. Okay, magnesium and sulfur. A metal, magnesium, and sulfur, a non-metal. Right, that would be ionic, okay? And thus, inside the molecule would be the forces called ion dipole. The next type is going to be dipole-dipole. Now, what does the prefix di mean? I'm saying all this talk about dipole. I'm pretty sure you're watching this like, Ms. Baldwin, I don't know what a dipole is. That's just a word you're saying. All right, di means 2, like 2 things, all right? Like you can have dioxide, 2 oxygens. Or divide, or like the word divide, 2 opinions, all right? Or numerator and denominator. So the prefix di means 2. Now, the other part of that word says dipole, all right? What do you think about when you think about a pole? North Pole? South Pole? Maybe a magnet? A plus end and a minus end? Hopefully, because that's what it is. Dipole means 2 ends or 2 regions. Right? 2 poles, like North Pole, South Pole, positive end and negative end. So a dipole has a positive end and a negative end. You want to know a great example of a dipole? It's water. All right? I'm going to draw water for you. Water starts with oxygen, and we're going to start with our Lewis dot. How many dots around oxygen? All right? It should be 6 dots. Hopefully you said that. If not, you might want to go back and study Lewis dot. So we have 6 dots. And where are those 2 hydrogens going to go? Oops, this ball is missing the dot. There we go. 6 dots. Now where are those 2 hydrogens going to go? You see the single dot sides? Good. That's where they're going to go. So I'm going to put an H here, and I'm going to put an H there. Okay, see that? That's how water looks. Now, this end of the molecule over here is going to be very, very negative because of these lone pairs, while this end of the molecule is not because there are no lone pairs. So this end is going to be what we call slightly positive, and this is going to be slightly negative. That's a little delta symbol for slightly. So you see how I have two ends? Okay? I have one end that's negative and one end that's positive. Oops, positive. Negative and positive. Dipole. Two poles. Get it? All right. Now, for this whole dipole-dipole business, the compound is going to have to be polar covalent. All right? So, first of all, it has to be covalent. So that means it has to be two nonmetals. All right? So like a carbon and a nitrogen, or a sulfur and a fluorine. Okay? It has to be on this side of the periodic table, two nonmetals. Now, how do I tell whether or not something is polar? That's a good question. Look back at water. Does it have lone pairs? See these little lone pairs? Put little ears on them. Those are the lone pairs left. If they're lone pairs over the atom that is in the middle, okay, then it is polar. Also, if it has a difference, if the atoms around it, let's say I have something that looks like this, okay? Give me a second. Something that looks like this. You see it? Carbon, does it have any lone pairs on the middle one? No, it doesn't. But the things around it, are they the same? Well, most of them, except one is what? One is fluorine. So because of that difference, this molecule is polar. So both of the things you see on the screen right now are what would be polar covalent. They're covalent because, are there any metals up here? No, they're all nonmetals. Carbon is a nonmetal and hydrogen is a nonmetal. All right? And hydrogen is a nonmetal, even though it's over here. And oxygen is a nonmetal. All right? So, since all these are nonmetals, and they're covalent because they're both nonmetals. Now, they're polar. This one is polar because it has a difference. It's not all H's around it. And this one is polar because it has lone pairs left on the central. So if it looks like that, it's a dipole-dipole. Now, we have a little extra thing involved in dipole-dipole. It's a specific type of bonding. It's called H bonding. H bond. Now, anytime you see a H with a F, a H with an O, or an H with an N, all right? Fun! That's going to be a hydrogen bond, okay? So that's our fourth, that makes four types. We have ion dipole, dipole-dipole, hydrogen bonding is the third type, H with the F, H with the O, or H with the N. The last type is London dispersion. Now for London, see if I can make some room up there, it has to be covalent like the other one, but instead of being polar, it has to be non-polar. Can you kind of see what I'm trying to write there? Right? So instead of being polar, it has to be non-polar. So I'm going to circle this. One is ionic, the other one is polar covalent, the other one is HFON, and the last one is non-polar covalent. Okay? So a non-polar covalent, all right? I'm going to go back to this example over here. Right now it's covalent because it has no metals, and it's polar because of this fluorine. But what if this fluorine changed into a H? And it will be methane. So it will be carbon. Everything around it is the same. There are no lone pairs in the central. So this compound, or this molecule rather, will be nonpolar. So the force at work in this one will be London dispersion. Right? However, the force in this one, in water, is going to be hydrogen bonding because of H with the O. Okay? This has been I Am Forces. I Am Forces. If you don't understand, don't just sit there, push stop, and rewatch the video. Okay? Love you guys. Baldwin's out.